Welcome to our latest video on the topic of reactions of transition metal ions with sodium hydroxide. This video is suitable for A-level students. By the end of this video lesson, you should be able to understand that precipitation reactions with aqueous sodium hydroxide can be used to identify the presence of Cr3+, Cu2+, Fe2+, and Fe3+ ions, and be able to describe these reactions with both chemical and ionic equations. You should also be able to understand that some D-block metal hydroxides are amphoteric and how these can be identified using the reaction of these hydroxides with excess sodium hydroxide. Now, in our previous videos, we've learned that a chemical property of transition metals is their ability to form transition metal complexes or complex ions. And we've learned that transition metal complexes are nearly always coloured, with almost every possible colour being observed in the wide range of complexes that exist. Now, we've also learnt in previous lessons that transition metal complexes tend to be either octahedral or tetrahedral, and examples of these complexes are shown on this slide. Now, it's the formation of the complex which leads to the colour in transition metal compounds, and in the absence of any ligands around the metal ion, the compound would be colourless. So, for example, copper sulfate is blue because it contains the CuH2O6 2+ ion. Now, as we've mentioned, transition metal compounds and solutions are coloured, and for the exam you have to be able to identify the presence of Cr3+ ions, Fe2+ ions, Fe3+ ions and Cu2+ ions by the colour of the precipitates on reacting with sodium hydroxide solution. Now, in aqueous solutions, these ions form complexes with water, so the addition of aqueous NaOH should really be thought of as a way of identifying the presence of the following complex ions: CrH2O6 3+, FeH2O6 2+, FeH2O6 3+, and CuH2O6 2+. So now let's recap what we mean by the term precipitation reaction. A precipitation reaction is a chemical reaction when two solutions are mixed and an insoluble solid forms. And a precipitate is this insoluble solid that forms from a precipitation reaction. Now, in this video lesson, the precipitates that we're going to form are going to be transition metal hydroxides. And we're going to form these by adding aqueous sodium hydroxide solution to aqueous solutions of transition metal ions. Now, the colour of these precipitates can help you identify which transition metal ions and transition metal complexes are present. Now, in addition to using aqueous sodium hydroxide solution as a chemical test for the presence of transition metal ions and complexes, we can also use aqueous sodium hydroxide here to test for amphoteric behaviour. Now, when we add aqueous sodium hydroxide to a transition metal ion or complex, we form an insoluble transition metal hydroxide. And these metal hydroxides have basic properties and will react with acids to form a salt and water. So, for example, copper 2 hydroxide would react with sulfuric acid to form copper sulfate and water. And the term amphoteric means having acidic and basic properties. In other words, it means it will react with both acids and bases. Now, to identify amphoteric metal hydroxides, all we have to do is add excess aqueous sodium hydroxide to the insoluble metal hydroxide precipitate. And if this precipitate dissolves in excess sodium hydroxide, we can assume that a chemical reaction has taken place, and the metal hydroxide is therefore classed as amphoteric. And this is because the compound is able to react with a base, and we already know that metal hydroxides would react with acids, so therefore we can conclude that if the precipitate dissolves in excess sodium hydroxide, the metal hydroxide is amphoteric. Now in the next section of this video, we're going to carry out experiments with aqueous sodium hydroxide. We're going to observe the different colour precipitates that are produced when sodium hydroxide reacts with transition metal ions. And we're also going to see if any of the transition metal hydroxides that we form are amphoteric. Now, as we carry out these experiments, we're going to complete the following table. It's important that you learn the different colour precipitates that form when you add OH- ions to these transition metal ions. Now, in addition to this, it's also important that you learn which transition metal hydroxides are amphoteric. Now, in this first experiment, we're going to put a few drops of chromium 3 nitrate, which contains chromium 3 plus ions, into a test tube, and then we're going to add a few drops of sodium hydroxide, and we end up with a grey-green precipitate. And then we're going to add excess sodium hydroxide to see if this precipitate dissolves. And as you can see, when we add excess sodium hydroxide, the precipitate dissolves, which shows us that chromium 3 hydroxide is amphoteric. So this slide summarises the results of this first experiment. So when we add aqueous OH- ions in the form of sodium hydroxide to a solution of chromium 3 plus, or more correctly CrH2O6 3 plus, we get a grey-green precipitate that forms, and this is chromium 3 hydroxide, and the precipitate dissolves on the addition of excess hydroxide ions, and this means that the metal hydroxide, chromium 3 hydroxide, is therefore amphoteric, because a chemical reaction has taken place when we've added alkali to the chromium hydroxide. We know it would react with acid, so because it's reacted with alkali as well and formed this soluble complex, we can class chromium 3 hydroxide as being amphoteric. Now, it's important that you can describe the reactions that take place between transition metal ions and aqueous sodium hydroxide with both word and chemical equations. So in this experiment, we added chromium 3 nitrate to sodium hydroxide. We made the grey-green precipitate chromium 3 hydroxide and sodium nitrate. Now, the chemical equation for this reaction is CrNO3 in brackets 3 plus 3 NaOH goes to CrOH in brackets 3 plus 3 NaNO3. Now, it's also helpful to include state symbols. So the state symbol of the two reactants is AQ, because we're adding aqueous solutions together. And the precipitate, chromium 3 hydroxide, has a state symbol S, because it's an insoluble solid. And the other product, sodium nitrate, is also aqueous, because it's a soluble salt. Now, you should also be able to describe the reactions that take place by using ionic equations. Now, this slide shows you that you're identifying the Cr3 plus ion with this reaction with NaOH. But it's more correct, really, to think of the reaction as a way of identifying CrH2O6 3 plus, the transition metal complex that forms when Cr3 plus ions are dissolved in water. Now, if we're going to write an ionic equation, we could write it as Cr3 plus 3 OH minus ions form the precipitate CrOH3. And the state symbols here would be aqueous for the two reactants and S, solid, for the precipitate that forms. Now, as I mentioned previously, It's more correct really to think of the Cr3 plus ion being surrounded by water ligands and forming a transition metal complex. So we can also write an ionic equation by using these transition metal complexes instead of just the ions. And if we do this, we would have the following equation: CrH2O6 3 plus 3 OH minus ions form CrOH3 H2O3 with this in brackets, and because we've kicked out 3 of the water molecules here by reacting it with 3 OH minus ions, the other product is 3 H2O. Now the state symbols are AQ for both reactants, S for the precipitate, and L for water because it's a liquid. Now when writing an ionic equation for a precipitation reaction, we only include the ions that form the precipitate, because the other ions, in this case the nitrate ion and the sodium ion, are spectator ions, as they don't take part in the main precipitation reaction. Now if we look at both ionic equations, we can see that the charges cancel out. So on the left hand side of both equations we have a 3 plus ion and 3 OH minus ions. This means that the 3 plus charge is cancelled out by the 3 minuses, and therefore the left hand side of both equations is neutral. Now on the right hand side we have CrOH3, which has no charge, and CrOH3 H2O3, which also is a neutral complex. So therefore the sum of the charges on both sides of the equations is 0. Now the other thing to mention here is that the oxidation state of chromium does not change during the reaction. If we look at the top equation, we can see that we have a 3 plus charge, so the oxidation state of chromium is plus 3. And when we form chromium hydroxide, CrOH3, the chromium is still a plus 3 oxidation state. Now this experiment also shows us that chromium 3 hydroxide is amphoteric. Now amphoteric substances have acidic and basic properties, which mean they undergo chemical reactions with acids and bases. Now we've already discussed that transition metal hydroxides would react with acids to form a salt and water. So chromium 3 hydroxide plus hydrochloric acid would form chromium chloride and water. CrOH3 plus 3HCl forms CrCl3 and 3H2O. Now when chromium 3 hydroxide is reacted with excess alkali, for example sodium hydroxide, the grey-green precipitate dissolves and forms a green solution. And this is because a chemical reaction has taken place. So this equation shows the chemical reaction that's taken place. Now the grey-green precipitate of chromium 3 hydroxide can be written as CrOH3 H2O3. Now you notice that it's still got a coordination number of 6 here. And this complex reacts with 3 OH minus ions to form CrOH6 3 minus, which is the soluble complex, the green solution that forms, and 3 water molecules, 3H2O. And this is a reversible reaction. Now once again, the oxidation number of chromium doesn't change here. It's plus 3 when it's CrOH3 H2O3, and it's also plus 3 in the CrOH6 3 minus complex. Now in examination questions, if you're asked to write equations to show that chromium 3 hydroxide is amphoteric, you must write equations to show its reactions with both acids and alkalis. It's no good writing just the equation to show the reaction of the green precipitate with excess hydroxide ions. You must write both equations. So now let's look at our second experiment. So here we're going to put a few drops of iron 2 sulfate into a test tube, and this contains the Fe2 plus ion, or more correctly the FeH2O6 2 plus ion, and we're going to add a few drops of aqueous sodium hydroxide, and you can see here that we form a dirty green precipitate. And when we add excess sodium hydroxide, this dirty green precipitate does not dissolve in excess sodium hydroxide. So that is telling us that this metal hydroxide is not amphoteric. So to summarize here, I've recorded this observation in the table, and you can see that the observation on the addition of OH minus ions is a dirty green precipitate being formed, and this is a precipitate which is iron 2 hydroxide. The precipitate doesn't dissolve on the addition of excess hydroxide ions, which proves it's not amphoteric. So this slide shows a word and chemical equation to describe the reaction that's taken place. So iron 2 sulfate reacts with sodium hydroxide to form the dirty green precipitate, which is iron 2 hydroxide, and sodium sulfate. And the chemical equation is FeSO4 plus 2NaOH forms FeOH2 plus Na2SO4. Now the state symbols here are Aq for both reactants, S for the precipitate, which is iron 2 hydroxide, and Aq for the other product, sodium sulfate. Now we also need to be able to write an ionic equation here. So remember, although this experiment is aimed at identifying the Fe2 plus ions, the Fe2 plus ions in water would form a complex with the water molecules and would exist as FeH2O6 2 plus. So there's two ways we could write an ionic equation here. We could either write it as Fe2 plus reacts with 2 OH minus ions, and the reason it's 2 OH minus ions is because there's a 2 plus charge on the ion, and this would form the precipitate, which is a dirty green colour, and this would have the formula FeOH2. Now the state symbols would be Aq for the reactants and S for the precipitate. Now the alternative way of writing the ionic equation is to use the complex ion here. So we have FeH2O6 2 plus, which would be aqueous, and this would react with 2 OH minus ions, also aqueous because we're adding two solutions together, and we would form FeOH2 and H2O4. Now it needs to be H2O4 because we still need a coordination number of 6, and this doesn't change in the reaction. Now when we form FeOH2, H2O4, we've kicked out 2 water molecules here because it was H2O6, and that's my other product. Now as the precipitate is an insoluble solid, it has the state symbol S, and water is a liquid, so it has the state symbol L. So now let's look at our next experiment. So here we're going to put a few drops of aqueous iron 3 chloride into a test tube. Now aqueous iron 3 chloride contains the Fe3 plus ion, or more correctly the FeH2O6 3 plus ion. So we're going to put this into the test tube, and then we're going to add a few drops of sodium hydroxide. Now when we add the sodium hydroxide, we form a rusty brown precipitate. And it's no surprise it's rusty brown because iron 3 hydroxide is rust. And when we add excess aqueous NaOH, the precipitate does not dissolve. And this is because iron 3 hydroxide is not amphoteric. So this slide summarizes the observation we've just seen. We form a rusty brown precipitate when we add aqueous NaOH, and this precipitate does not dissolve on the addition of excess hydroxide ions, and therefore the metal hydroxide is not amphoteric. So now let's describe this reaction with a word equation and a chemical equation. So we have iron 3 chloride reacting with sodium hydroxide, forming the precipitate iron 3 hydroxide and sodium chloride. And the chemical equation is FeCl3 plus 3 NaOH makes FeOH3 and 3 NaCl. Now we also need to be able to describe this reaction with an ionic equation. So once again I can write the ion as either Fe3 plus or the complex ion FeH2O6 3 plus, because the Fe3 plus ion in water would form a complex with water surrounding the Fe3 plus ion. Now when writing the ionic equation, I can either write the ionic equation as Fe3 plus, and this is aqueous, reacting with 3 OH minus ions. Again, this would be aqueous because we have a solution reacting with a solution, and we would form the precipitate, which would be FeOH3, and that would be a solid. And if we wrote this ionic equation using complex ions, it would be FeH2O6 3 plus, and this would react with 3 OH minus ions, and when it reacts with 3 OH minus ions, we would form the complex, which would be FeOH3 and 3H2O, because once again the coordination number doesn't change in this reaction, so it still must add up to 6. So we've got FeOH3, 3 OHs and 3 waters, adding up to 6 ligands surrounding the ion. So the 3 OH minus ions kick out 3 water molecules, and we have our overall equation. So the state symbols are AQ for the reactants, S for the precipitate, and L for water. So now let's look at the reaction of aqueous copper 2 plus ions and aqueous sodium hydroxide. So if we put a few drops of copper 2 plus into a test tube and add a few drops of aqueous NaOH, we form a pale blue precipitate. And if we then add excess aqueous NaOH, this pale blue precipitate does not dissolve. So this is telling us that copper 2 hydroxide is not amphoteric. So viewing this experiment allows us to complete our table. So the last observation is that when we add OH minus ions to a solution of Cu2 plus ions, we form a pale blue precipitate, and this precipitate does not dissolve on the addition of excess hydroxide ions, and therefore the metal hydroxide is not amphoteric. So once again we can write word, chemical and ionic equations to describe this reaction. So we have copper 2 sulfate reacting with sodium hydroxide to form the pale blue precipitate copper 2 hydroxide and sodium sulfate. The chemical equation would be CuSO4 plus 2 NaOH forms CuOH2 and Na2SO4. Now once again we can write an ionic equation to describe this precipitation reaction, and the complex ion here would be CuH2O6 2+. This is a transition metal complex that forms when copper 2+ ions are dissolved in water. So we can write our ionic equation as either Cu2+, and this is aqueous, plus 2 OH- ions, which is also aqueous, forming the pale blue precipitate, which has the chemical formula CuOH in brackets 2, and this is a solid, so it has the state symbol S. And we can also write this ionic equation as CuH2O6, and this has a 2+ charge, and this will react with again 2 OH- ions, to form copper 2 hydroxide, which would have the following formula: CuOH2, H2O4, and it has 4 waters here because the coordination number must still be 6 during this reaction. And when we bond 2 OH- ions to the copper 2+, we kick out 2 waters, so that's my other product. And I'm going to put in the state symbols: AQ for both reactants, S for my precipitate, and L for water. So just to finish up, we're going to do one further experiment where we put a few drops of Zn2+ solution into a test tube, and we add a few drops of aqueous sodium hydroxide, and this time we get a white precipitate. And when we add excess sodium hydroxide, this precipitate will start to dissolve. We'll add a little bit more here because it's starting to dissolve, but it's not fully dissolved yet. And then we're going to add a bit more of the aqueous sodium hydroxide, and we may need to shake it up here to get the precipitate to dissolve. So if we shake the test tube, the precipitate is almost dissolved here, and we may need to add a few extra drops of aqueous NaOH just to make sure that every last bit of precipitate dissolves. So we're going to add a few more drops of aqueous NaOH here, and we're going to shake up the test tube, and you can see now that the white precipitate has fully dissolved to form a colourless solution. Now, zinc is a D block element, but it's not classed as a transition metal as it does not have atoms or stable ions with a partially filled D shell. Now, when a solution containing Zn2+ reacts with aqueous sodium hydroxide, we've seen that a white precipitate forms, zinc hydroxide. Now I can describe the reaction that takes place with an ionic equation, and this would be Zn2+ plus 2OH- forms ZnOH in brackets 2. The state symbols would be AQ for the reactants, and the precipitate would have a state symbol of S. Now, as zinc is not a transition metal, I can just simply write the ionic equation in this form. Now, zinc hydroxide is amphoteric, and this is because the white precipitate dissolves in excess sodium hydroxide to form a colourless solution. And if we have to show, using equations, that zinc hydroxide is amphoteric, we need to write 2 equations, one with a zinc hydroxide reacting with acid, and one with a zinc hydroxide reacting with alkali. So with acid, I could write the following equation: ZnOH in brackets 2 plus 2HCl, if I use hydrochloric acid as my example of an acid, would form ZnCl2, zinc chloride, plus 2H2O. And with alkali, the equation would be ZnOH in brackets 2 plus 2NaOH forms Na2ZnOH in brackets 4. And it's this Na2ZnOH OH in brackets 4 compound that is our colourless solution. Now the name of this compound is sodium zincate, and the formation of this colourless solution shows that zinc hydroxide reacts with alkali. We know that zinc hydroxide is a metal hydroxide, would react with acid, so therefore we can conclude that zinc hydroxide is amphoteric. So we've seen in these experiments that chromium 3 hydroxide is amphoteric, and that's the only transition metal hydroxide that you need to learn that is amphoteric. However, the D block hydroxide, zinc hydroxide, is also amphoteric. So now let's test your understanding of what we've learned in this lesson with some practice questions. This first practice question is made up of 3 parts. The first 2 parts are on this slide. So read through the question, pause the video, have a go at the first 2 parts of the question, and then we'll have a look at the third part of the question. So here's the last part of this first question. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers to the whole of question 1. So question 1a is asking you to use the convention of representing electrons by arrows in boxes to give the electronic configuration of an iron 3 ion, Fe3+. Now, iron's electron configuration ends in 3d6 4s2. So iron 3+ will be 3d5. So the electrons fill the orbital singly before they pair up. So this is what the electron arrangement looks like. There's one electron in each 3d orbital. If you had the correct electron configuration, you get 1 mark. Now for part 2, you're asked to describe what is seen when an aqueous solution of sodium hydroxide is added dropwise to a solution containing Fe3+ ions until an excess of sodium hydroxide is present, and you should give an equation for any reaction that occurs. Now you'll get a rusty brown precipitate forming. Now if you said brown, yellow or red as a colour, you get half a mark, and if you said precipitate, you get half a mark. Now this precipitate is insoluble in excess NaOH, and if you mention this you get another mark. And for the equation, you could either write Fe3+ plus 3OH- ions form FeOH in brackets 3. State symbols aren't required here, but this would get you a mark if you wrote this equation down. However, you could also write the equation in complex ion form and write down Fe H2O6 3+ plus 3OH- ions form FeOH in brackets 3, H2O in brackets 3, plus 3H2O. Now in part B, you're asked to describe how aqueous sodium hydroxide could be used to distinguish between aqueous iron 2 sulfate and aqueous iron 3 sulfate. So if you added aqueous NaOH to both, you would get a dirty green precipitate with iron 2 sulfate, and you would get a rusty brown precipitate with iron 3 sulfate. And there's 1 mark each here for each observation. So here's our second practice question, and once again there are multiple parts to this question. So parts A and B are on this slide. So read through the question, pause the video, have a go at it, and then we'll look at the next parts of this question. So here are the last 3 parts of question 2. So once again, read through the questions, pause the video, have a go at them, and then we'll go for the answers. So now let's go through the first parts of question 2. So Question 2 says chromium forms amphoteric compounds. State what is meant by the term amphoteric. Well, amphoteric means it reacts with both acids and bases or behaves as an acid and a base. And if you said this, you get 1 mark. Now in part B, you're asked to use arrows in boxes to show the electronic structures of the chromium atom and the Cr3+ ion. Well, chromium's a regular, so it ends in 4s1 3d5. And chromium 3+ would therefore end in 3d3. 1 mark for each correct electronic configuration. Now for C part 1, you're asked when aqueous sodium hydroxide is added to aqueous chromium 3 sulfate, a precipitate is formed. What colour is this precipitate? If you said it's green or it's grey-green, you get 1 mark. And for part 2, it says describe what happens when excess NaOH is added to this precipitate. Well, the precipitate dissolves to form a green solution. If you said that, you get 1 mark. And for the last part, it says write an ionic equation to describe this reaction in part 2. And this is a 2 mark question. So the ionic equation would be CrOH in brackets 3, H2O in brackets 3, plus 3 OH minus ions forms CrOH in brackets 6, 3 minus, plus 3 H2O. If you said that, you get 2 marks. 1 mark for the reactants being correct and 1 mark for the products being correct. So that concludes this video lesson. So after watching this video, you should now understand that precipitation reactions with aqueous sodium hydroxide can be used to identify the presence of Cr3+, Cu2+, Fe2+, and Fe3+ ions, and be able to describe these reactions with both chemical and ionic equations. You should also be able to understand that some D-block metal hydroxides are amphoteric and how these can be identified using the reaction of these hydroxides with excess sodium hydroxide. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.